Here we have A and B. Each of them have distinct eigenvalues. And one thing that we showed was, well, did we show it? Well, it's kind of obvious that if you have distinct eigenvalues, for each eigenvalue you have eigenvector, at least one eigenvector. And because of that, you're going to have a basis of eigenvectors if you have any matrix that has distinct eigenvalues. Which means under that basis, if you rewrite the matrix A under that basis of eigenvectors, you end up with a diagonal matrix. You remember that, right? If you write A under that basis B, where B is all the eigenvectors, and A times anything in here will give you lambda 1 times V1, something like this, so that A acts on this basis vectors as a diagonal matrix. It just multiplies by a constant. So this will eventually just become like lambda 1, lambda 2, lambda n. So having distinct eigenvalues is one condition where you know that the matrix can be diagonalized. So let's say you have such a matrix, and let's say they commute. Then any eigenvector of A is an eigenvector of B. And vice versa, because A and B are symmetric. If you switch A and B, that also means that any eigenvector of B is also eigenvector of A. So let me give you that proof. And proof goes like this. Let's say let V be an eigenvector of A. In other words, A times V is, say, some lambda times V, some eigenvalue lambda. Then A times B times V, let's try this, A times B times V, would equal to B times A times V, because A and B commute, right? But AB is same as BA, so I can commute them. And that gives you B times lambda V, which gives you lambda times A times V. No, B times V, sorry. Because the lambda is a number, I can switch. Numbers commute with any matrix. So lambda can be put in front, and I can do this. From here to there, I'm just using the fact that AV is lambda V. So I'm just replacing AV as lambda V. And then B times lambda V, I can just pull the lambda out, and I do this. Oh, wait, that means that BV is an eigenvector of A with eigenvalue what? Eigenvalue lambda. Isn't that right? Because BV is a vector, right? If you multiply a matrix with a vector, that's a vector. Look what we just found. A times BV is lambda times BV. That's exactly the eigenvector equation. And it has the same eigenvalue as before. Uh-oh, that's bad. Why? Because then if B, so, but if BV is linearly independent of V, right? If these are pointing at different directions, then now you have two distinct eigenvectors with the same eigenvalue, which violates this principle, right? If you have distinct eigenvalues, you can't have two distinct eigenvectors. I mean, if you take any eigenvector and multiply by a constant that's non-zero, that's again an eigenvector. That we know, right? But that doesn't give you a new direction. If you have distinct eigenvalues, then that means that each eigenvalue will have exactly one subspace of eigenvectors. Yeah, it's a bit tough for me because I skipped the part about eigenspaces. So if you have eigenvalues of multiple eigenvectors pointing in different directions, then you can talk about eigenspaces, where eigenspaces now is two-dimensional for that eigenvalue and stuff like that, but I skipped all that. Yeah. Those are only for technical proofs. We don't need it in this class. But what I'm trying to say is that if BV is linearly independent of V, then lambda would be a repeated eigenvalue of A, because you have two distinct eigenvectors pointing at different directions with the same lambda, which would be a contradiction. Yeah. Therefore, so BV must be some multiple of V. They have to be pointing at the same direction. They have to be linearly dependent. So let's say A times V. But what is that? BV equal to AV for some A, real number A, right? Well, what does that mean? This means that V is an eigenvector of B with eigenvalue A. Right? V is an eigenvector of B with eigenvalue A. Okay. So, there's a corollary that's also interesting from this, which is that corollary. Such matrices A, B are simultaneously diagonalizable. Okay? And what does that mean? That means there exists a basis A that there exists a basis B, script B, where both matrix A and B are diagonal for the same basis B. That's because they share the same eigenvectors. Right? If they share the same eigenvectors, and if it has distinct eigenvalues, then you have bases of eigenvectors, and with respect to that basis, they're going to look, both of them will look like a diagonal matrix. Okay? That's what it means. Yes?
So this is saying there are like multiple sets of eigenvalues with the same eigenvectors?
No. Distinct eigenvalues means that for each eigenvalue there should be only one eigenvector.
Okay.
Yeah. This really means, you know how to find the eigenvalues, right?
Yes.
You take the determinant of this equal to 0. This is a polynomial of lambda. And sometimes polynomials have eigenvalues of, or zeros that are repeated with multiplicities. But here I'm saying that this is a polynomial where all the zeros are just written once. It's not repeated ever. Okay? Which is like the more generic case. And then that in that case, and if two things commute, then they can be diagonalized at the same time. Yes?
So you're saying matrix A of B and matrix B of B, they're both diagonal?
They're both diagonal.
Okay.
They're both diagonal. Now let me say a little bit more about that. So if I say that A is really written in some basis, think about this A as the basis using the standard unit vectors, like 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0. Let's say that exists in the space, and if you write it, then this is the matrix that you get. Okay? Then writing A with respect to this new basis of eigenvectors is same thing as, well, by the way, when I say this, I really mean A to A. That's the symbol that we're using. So this is really B to B. This is so B goes to A goes to A, and then A goes to B. So if B goes to A and then A goes to A and then A goes to B, then B goes to B. Right? Starts at B and ends at B. Right? And usually we denote this as our P, matrix P, and this will be inverse of this one, because what it does is it does the opposite, right? So literally, if you calculate this matrix and then calculate the inverse of this matrix, you're going to get this, right? And this, we said this is A. And because I'm claiming that this is a diagonal matrix, let's write D for that. So another way to say that this is a diagonal matrix is to say that P inverse AP is diagonal. And being simultaneously diagonalizable means that the same P can be used to diagonalize B. So it will be like D2, another matrix. Another diagonal matrix, and the important thing is that the same vector, the same matrix P can be used to diagonalize both of them. Okay? Now, this actually happens in general. So the general theorem, which is, we didn't do enough theory to prove this one, but it kind of, this work kind of supports it. It says that if A, B are both diagonalizable, then, and AB is equal to BA, if they commute, then A and B are simultaneously diagonalizing. Okay. Now this is a harder theorem to prove than what we just proved here, because the same argument that we were using doesn't hold here. So, but you have to talk about eigenspaces and stuff like that in order to make this work. It can be done. What's not true is that if A and B are not, if any of these are not diagonalizable, it doesn't mean that being commuting implies both of them being diagonalizable. So You have to know beforehand that they can be separately diagonalized, but if they are and they do commute, then they have to be simultaneously diagonalized. Another thing is, say, if you have two diagonal matrices always commute, right? So we also know that D1, D2 is equal to D2, D1 for diagonal matrices. And if you replace these by these, plug in both sides, what do you get? We get P inverse AP, P inverse BP equals to P inverse BP, P inverse AP, and then these two cancel. The P and P inverse, when they multiply, they cancel. And then I can multiply P on this side to cancel these two. I can multiply P inverse on this side to cancel those two. Then what you get is that AB has to be equal to BA. So this is the converse is also true. Okay? If A and B are both diagonalizable, and if they are simultaneously diagonalizable, then they must commute. That's another thing. Now, this one has another important corollary, which has some application in quantum mechanics, but I guess that's just too much for this class. So, if A, B are Hermitian, okay. Hermitian meaning that i.e. A is equal to A transpose and then bar. Okay. Same thing for B. Okay. And AB equals to BA, then A and B are simultaneously diagonalizable. Mostly diagonalizable. And that's because of the spectral theorem. Because of the spectral theorem, we know that anytime a matrix is Hermitian, then you can diagonalize it using unitary matrices. Right? So you know that A, you can take a matrix U and U transpose bar. This happens to be the inverse of this one. If that's what unitary means. And this will be a diagonal matrix. So that's called the spectral theorem. And because of spectral theorem, we know that A and B are Hermitian means that they are both diagonalizable, and then this theorem can immediately apply to give you the other results. Okay?